In this video, we're going to derive two methods for performing numerical integration. The first, the trapezium or trapezoidal rule, is a first-order method, and the second, Simpson's rule, is second order. In my previous video, definite integration, we saw that we can find the area under a curve by performing definite integration, which provides an exact solution because it's an analytical method. However, there are some circumstances in which we can't do this, and we have to resort to approximate methods for finding the area under a curve. Suppose we want to find the area under this curve between two x values a and b, and suppose that we know values of the function between a and b but can't integrate. One thing we can do is discretize by breaking up the domain between a and b into a number of smaller segments. Thus, for example, we could divide it into 4 areas as shown here. Let's suppose that we have 5 x coordinates and 5 corresponding values of the function. We could approximate each of these areas using a trapezium, which has corners corresponding to the x values and the known function values. If we sum up the areas of the 4 trapezia, it provides an estimate of the area under the curve. It's clear that if we take smaller intervals and thus more trapezia, this estimate will improve. For example, here we have doubled the number of points. Let's think how we would proceed by first considering a single trapezium of width h. Okay, so here we have a single trapezium with width h and dimensions y0 and y1 in the y direction. The area of the trapezium is a half h times y0 plus y1. Now let's add a second trapezium of the same width. The second trapezium has dimensions y1 and y2 in the y direction, and thus has area a half h times y1 plus y2. If we add these together, we have a1 plus a2 equals a half h y0 plus y1 plus a half h y1 plus y2. If we bring these two brackets together, we can see that the central value of y, y1, appears twice because it's a side length of both trapezia. Thus we have a half h times y0 plus 2y1 plus y2. If we now add a third trapezium, we can see that the total area equals a half y0 plus 2y1 plus 2y2 plus y3. We can see that as we add more trapezia, the end y values are always going to appear once, and the y values in between will appear twice. This gives rise to the trapezium rule. We have the area A equal to a half h times y0 plus 2 y1 plus y2 plus all the y values up to yn minus 1 plus yn, where we have a spacing of fixed width h and n plus 1 points numbered from 0 to n. We describe an approximation of this type as a first-order approximation, and it corresponds to a simple linear interpolation between each pair of points on the curve. Let's turn now to a higher-order approximation. One way to do this is to consider 3 points at a time rather than 2, and to fit a curve through those points. To set up a method, I'm going to take 3 points evenly spaced, again using h as the distance between points. Sticking with a polynomial type approximation, the lowest order curve that passes through 3 points is a quadratic. Let's consider the area under a quadratic function passing through the points minus h y0, 0 y1 and h y2 as shown here. The curve will be described by a function of the type y equals ax squared plus bx plus c. We are first going to find the area under the curve and then use the points through which we know it passes to express the area in terms of A, B and C. To find the area, we have to integrate. We have A equals the integral between minus h and h of ax squared plus bx plus c with respect to x. Performing the integration yields a third ax cubed plus a half bx squared plus cx, and we have upper limit h and a lower limit minus h. Putting in these limits yields a third ah cubed plus a half bh squared plus ch minus a third ah cubed plus a half bh squared minus ch, which gives us 2/3 ah cubed plus 2ch. Tidying this up, we have the area equal to a third h times 2ah squared plus 6c. We want to write A in terms of y0, y1 and y2, which means unravelling 2ah squared plus 6c. To do this, we look at the coordinates of our 3 points. We have y0 equals ah squared minus bh plus c, y1 equals c, and y2 equals ah squared plus bh plus c. Adding y0 and y2, the bh terms cancel, leaving 2ah squared plus 2c. Well, we're nearly there now. To match the expression 2ah squared plus 6c, we just need to add 4c, and we know that y1 equals c. Thus, we have y0 plus 4y1 plus y2 equals 2ah squared plus 6c. Thus, the area under the curve can be written a third h times y0 plus 4y1 plus y2. Looking at this expression, we can see that it depends only on the width of the spacing h and the y-coordinates of the 3 points. It doesn't matter where the y-axis is. Thus, this provides the basis for a second-order method for estimating the area under a curve. Thus, for example, if we have a curve passing through 5 equally spaced points, we can estimate the area under the curve using 2 quadratic approximations of this type. As with the trapezium rule, we can see that the common end value, which in this case is y2, appears twice. Thus, we have the total area A equals a third h times y0 plus 4y1 plus 2y2 plus 4y3 plus y4. As we add more intervals and areas, a repeating pattern emerges. For example, here we have 9 points and 4 areas. We can see that the common endpoints of each area appear twice, i.e. the internal even-numbered points y2, y4 and y6, and thus we have this formula for the area. We see here that the 2 endpoints, y0 and y8, appear once, and the coefficients of the internal points alternate between 4 and 2, starting with 4. Note that the number of points must be odd and the number of intervals even. If we number from 0, as we have here, then we often number the last point as 2n, in which case n is the number of areas we are adding together. Thus in this case, n equals 4. In general, we have this rule, which can also be written A equals a third h times y0 plus 4 times y1 plus all the odd-numbered y values plus 2 times y2 plus all the even-numbered y values up to y2n minus 2 plus y2n.